Okay, in this video we're going to look at a concept called relative velocity. Now when we do problems in physics, we typically use a reference frame of the Earth, right? We live on the Earth. The Earth relative to us, even though it's spinning at a high rate of speed and also rotating or orbiting around the sun at a high rate of speed, we don't notice that because everything is moving at the same speed. So for us, it seems like the Earth is at rest. So this becomes our typical reference point. So if we're driving down the highway at 55 miles per hour, let's say, that 55 miles per hour is a relative speed to the Earth, right? It's 55 miles per hour to the reference point of the Earth. If the Earth is at rest, then we're moving 55 miles per hour relative to the Earth. So what if, though I'm driving down the highway and another car comes by and he passes me, he or she, at 70 miles per hour. So let me draw this vector a little bit longer. Now, how fast is that car moving relative to me? If I'm in my car and I observe this car, do I see the car moving 70 miles per hour? Or do I see the car moving 15 miles per hour? Right? And if you've ever been in this scenario, you would think, well, the car only appears to be moving 15 miles per hour from my reference frame, from the reference frame of my car. So in this little part of the unit, we're going to look at how can we determine the velocity of objects from other reference frames besides just the Earth, moving reference frames. Now I want to throw a side note in here before I continue with the example. Are we talking about Newton's laws, or are we talking about the laws of Einstein? So this is a first physics course. We're dealing with classical mechanics. We're dealing with classical physics, primarily dating back to 16s, 17s, and pre-1905 or late 1800s when really things began to shift. So I'm going to throw in a little side note here. Okay. So the important thing about this side note, I think it's interesting, it's worth mentioning, but it's not going to be on the test. What we're really dealing with is Newton, right? The laws of Newton. And the laws of Newton, we're going to get into in the next unit, Newton's three laws, really define how and why things work in classical physics. And this works for really small speeds and for really, larger objects. When we get into the micro level, to the atomic level, and to really high speeds, we'll see the rules of physics change. So, what am I talking about? I'm talking about Galilean transformations here. Galilean transformations are based on Newtonian relativity. So the main idea that Newton had was that there was an absolute time and space to the universe. So if I were here, or if I were on Pluto, or if I were in the Alpha Centauri neighborhood, there would be an absolute time, right? We would all say it's 12 o'clock at the same time, right? And then there's also absolute space, that space is fixed, right? I can't move space. Space is always, like if I were to plot out a grid throughout the whole universe, that there's an equally spaced grid that everyone experiences. And this really, for those of you who have studied the Enlightenment, this is a deterministic worldview that dates back to the Enlightenment. So deterministic in the sense that if there's absolute time and space, and if I know the initial conditions of some object, where it's going and how fast, I can have absolute certainty to predict where it's going to be at any future time. So this is the way that people saw the world for a few hundred years. There's another type of transformation in terms of relative velocity that this is not, but that gets a little interesting. If you ever heard of a Lorentz transformation, or if you get to a physics course in college, those of you that are going to be engineers or physics majors or somewhere along those lines, heavy science majors, you might take a course where you learn a little bit about special relativity. So what happened in the late 1800s, when they determined that the speed of light, that light was actually an electromagnetic wave, this was Maxwell, James Clerk Maxwell, in the mid-1800s, they figured out that light was an electromagnetic wave. We'll learn about that second semester. And they began to realize that the speed of light didn't change in any reference frame. It didn't matter. If you were moving, if you were not moving relative to the Earth, you would always measure the exact same speed of light. And this led Einstein to one of his first most brilliant insights in 1905, and that was his special relativity theory. So the special relativity theory basically says there is no absolute time and space. That time and space are relative to each individual observer, and that if you're moving at a really high rate of speed, time actually contracts. There's time contraction and length, or time dilation and length contraction. Time slows down, length gets smaller when you're moving at really high rates of speed. So this is a sidebar. We're not talking special relativity, we're talking Newtonian, where at very small velocities relative to the speed of light, now just to kind of show you where this comes from, right? A Lorentz transformation, this is the factor that would shift based on special relativity. C is the speed of light, 300 million meters per second, very fast, never changes in any reference frame. And this little v here is the velocity of a moving reference frame. So if this v is small relative to this number, this becomes 1, and we don't really notice the effects of special relativity. But when you have things moving at really fast rates of speed, right, we got to account for that, and that gets into special relativity. So that's a little sidebar. Hopefully you found that a little bit interesting. If you go into future courses, you'll learn more about it. But for now, we're dealing with a Newtonian worldview where things are fairly simple to predict. All right, let's go back to our car. Let's look at two scenarios. So my car is moving down the highway at 60 miles per hour, and big truck comes by, and the truck is moving at 90 miles per hour. Okay, so these are relative to the Earth velocities. But I want to know, what's the velocity of the truck relative to my car? And so to figure that out, we're going to use a little bit of a vector trick. What we do is we line up the vectors. So I didn't line these up really well. So I'm going to line up my car vector. Velocity of car is 60. And then I'm going to line up my truck vector, starting at the same spot. Okay, and if I want to know how fast is the truck moving relative to my car, I simply determine what's the velocity that would connect, the velocity vector that would connect my car to the truck. So in this case, the velocity of the truck relative to the car is the velocity of the truck. I should be using my vector symbols minus the velocity of my car relative to the Earth. So I would say, relative to my car, the truck is moving 30 miles per hour. Okay, well that seems easy enough, but what if my car is moving in the opposite direction of the truck? So in this case, my car is moving 60 miles per hour to the right, and my truck is going to move 90 miles per hour to the left. How do I deal with it now? Well, we're going to do the same thing we did here. We're going to start with the two vectors. Velocity of the car is to the right. And now I'm going to line up my truck velocity at the same, starting at the same spot, and draw it in the opposite direction. So the velocity of the truck is 90 miles per hour to the left. You can call it negative. I think that's a good habit to get into, because in a reference frame, there's always a direction that matters, right? To the right, up, left, negative, so forth and so on. All right, so now to figure out how fast is the truck moving relative to the car, I start at my car, and then I draw the vector that connects the front of the car to the front of the truck. Now, how long is this? Well, really, velocity of the truck relative to the car now is the same formula, right? The velocity of the truck, which is negative 90, minus the velocity of the car, which is positive 60. So, in this case, I get a negative 150 miles per hour. So, what does this mean? Well, what this means is, if I'm in the car and the truck's heading at me at 90 miles per hour, it's as if I were stationary right? If I were stationary and the truck was moving at 150 miles per hour past me, okay? Now what about the velocity of the car relative to the truck? What if I'm sitting in the truck? What if I'm in the truck's reference frame? How fast is the car moving relative to me? Well, we could do the same thing, but now we just draw the vector from where the truck ends to where the car ends. So we draw it in the opposite direction. And we would see that this is 150 miles per hour, but positive. Well, does that make sense? Yeah, because if I'm driving in the truck at 90 miles per hour, if I were stationary, it would take my speed plus this car's speed. It would appear that the car was moving 150 miles per hour, but in the positive direction, right? Because I'm moving negative, the car is moving positive. So the velocity of the car relative to the truck is just the opposite. Okay, so these are some simple examples of relative velocity in one dimension. In the next video, we're going to show you how to deal with relative velocity when we have multiple dimensions or two-dimensional vectors in play.